Okay, let's go on to our third and final application of the afternoon. It's on the topic of wireless communications. And it's not in the realm of RF, as you might be thinking from all the things we talk about today. It's in the area of light. So our next speaker has invented a term called LiFi and gave a TED Talk recently that's been seen by more than 1.4 million people. He's also popped up on several news networks talking about the future of wireless communication and how all of us might be reading our internet traffic through light instead of wireless RF signals very soon. To tell us more about that, please welcome to the stage Professor Harald Haas from the University of Edinburgh.
Good afternoon, ladies and gentlemen. Thank you, Kyle. It's my big pleasure to talk about the spectrum crunch, the radio frequency spectrum crunch in wireless communications, and how light can come to the rescue. In order to illustrate the scale of the problem, I've basically only provided you with a list of statistics that you can find on the YouTube website. There's basically every minute there are 3 days of video content uploaded to the YouTube website. There's more video content produced in 1 month than in all 3 major US networks in 60 years. And even in 2011, there were basically 140 clicks and uploads per person on this planet. And the interesting thing about that is most of that video is nowadays, with the advent with a smartphone, done by mobile phones. And that video traffic is growing at a compound annual growth rate of about 50%. And so what does that mean to our wireless communication networks? So on the right-hand side here, I've plotted a graph from Qualcomm that shows the different mobile communication standards from around 2000, where we had GPRS, we had Edge, we had wideband CDMA, and now we have LTE, and now LTE Advanced, and 5G is on the horizon. And these systems, in the latter one, use MIMO, multiple input, multiple output. And on the x-axis, you see all these different systems. On the y-axis, you see the spectrum efficiency. That is the number of bits per hertz bandwidth that can be used or can be transmitted in these systems. And while there's a tremendous improvement from 0.03 to 1.4, we still see a saturating trend. Despite tremendous investment into research and development in MIMO, in all these kind of fancy new technologies, still in a network we see a saturation, and that is primarily because of interference. On the other hand, an independent trend is what I've just described with the example of YouTube, is the tremendously growing mobile data through the networks, which is here shown and illustrated by a graph from Cisco, and where they expect in 2016 around 10 exabytes, so 18 zeros, per month through the networks. And that is basically an exponential trend. Now, it doesn't take a lot deal of science when you try to match these two trends. There is something happening around now, which is we call a spectrum crunch. We're running out of radio frequency spectrum. So while, as a scientist, a researcher, you're very happy to find problems, but we also want to propose solutions. And what are the solutions? For me, they're fairly simple. Either you find new spectrum, and that's happening while I'm standing here, or you make better use of the existing spectrum, hence reuse the frequencies more often spatially, which means smaller cells. And the small cell concept was the main contributor for that steep increase in the spectrum efficiency I've shown with the previous slide. So take this in very, very simple two measures. So how do we go about that? I think we need to open up the box and try to unwind if you're an RF engineer, thinking of your RF world. If we look into the entire electromagnetic spectrum, there is even gamma rays. So it links to a previous talk here. We also have the terahertz. We have infrared, visible light spectrum, ultraviolet light. And interestingly, if we take the entire radio frequency spectrum, say up to 30 gigahertz, which includes millimeter wave, a trend that's been currently seen now, included already. But in that entire 30 megahertz, if you multiply that by 10,000, you end up in the entire spectrum that you have in the visible light region. So things that illuminate me at the moment from the ceiling. And these lights in this spectrum is, by the way, unregulated. No government has any fingers on it. There's no spectrum auction to be expected from that spectrum. It's safe, it's free, and it's already there. And then we have had the incandescent light bulb, obviously, but now with the tremendous development since 1993 with the blue chip, LED chip, now we have the white LEDs, basically conquering the markets, and we see a revolution of LED lights in cars, in reading lamps, in aircraft, in everywhere. And LEDs are electronic devices, and as such, they can be treated as electronic devices, so they can illuminate, but at the same time can be switched on and off very quickly, and hence they give us a lever to use them as data communication device. So we, in the future, I've coined LiFi at TED 2011, and LiFi is basically a light bulb, a network light bulb, providing hundreds of megabits, and I'm quite proud to say that in the research lab we now have achieved via an incoherence or non-laser light, we have achieved 3.5 gigabit per second with headroom to higher rates. So 3.5 gigabits per second with an LED. But that is not yet networking. That is link level, so point to point. But we want to use that as a network, and I've coined that term Autocell network. Some of you may be familiar with femtocells, which are the very small cells, but if you take it one step smaller, it's the Autocell, and we call it the optical Autocell network. So what is this about? What is an optical Autocell? Let's start where we are at the moment. We have here an office environment, for example, and if you want to cover the office environment, we would install one Wi-Fi access point, maybe two, maybe three, to cover the entire building. So there are a few things going on at the moment. There's LTE is running out of spectrum. There's lots of offload into Wi-Fi. You see this via hotspots and so on. And secondly, these hotspots, as indicated by the different colored rings, have a decreasing data rates at the cell boundary. In the cell boundary, what happens as well is you see the signal from the other hotspot. And that's causing interference, and interference basically pushes down the throughput. And interference, as I said, in a small cell environment is one of the main problems for enhanced spectrum efficiency. But that office environment that is shown here also has ceiling lights. And ceiling lights are, like here, fairly equally spaced. So why don't we consider existing lighting system with a honeycomb like this as an optical Autocell network where the light serves you as an access point, serves multiple users, and you move from one light fixture to another one, your session will be transferred as a handover, so networked Wi-Fi. And not only that, that light in this room here wouldn't be penetrating into the other room. There's zero interference from here to there. But not only that, if you take a classic boardroom or room like this, where you have multiple lights at the ceiling, there's the possibility that you have at the opposite corners an access point where the signal, where the light cone wouldn't interfere with the light cone at the other corner, so you could more aggressively reuse the same spectrum even in a room. So if this access point gives you 100 megabit and you have 10, you can multiply. It is an increase in the data rate even within a room. And there's always the problem of the question is how do you get the data to the lights? So that the lights, in order for them to illuminate, require power. So it is well-known standard like power line communication, or even if you have new installations, you use power over Ethernet, where the power comes through the data. 60 watt in a light bulb is typically 5 watt. So we have an Autocell network, which first of all saves you a big money in terms of the energy bill. So we want that, so that's a driver for it. And secondly, the Autocell network would not require new installation. It would use existing infrastructure quite neatly. So here comes a little bit of an investigation. Part of our research we've done is we have considered an LTE macrocellular network with these hexagonal cells. And in the middle or somewhere, there's an office block of 5,000 square meters. It has corridors, and there are femtocell access points spread around on the corridors. The green points there indicate the femtocells. And then you see, indicated with one room, we have this lighting system that would serve our Autocell network in the room. And what we have done is we have compared the spectrum efficiency per square meter. So how many bits per second per hertz per square meter could you get from these two different systems? And we varied the number of femtocells in a floor up to 20 in a 5,000 square meter office environment, and have then taken the ratio between the area spectral efficiency of the femtocell network, which suffers from interference from the macrocell base station and vice versa, whereas light wouldn't suffer from that interference, and have found that in the best case, with 4 femtocells in that environment, we have in office rooms of 2.5 by 5 meters, we see up to 900-fold improvement in the spectrum efficiency. So if you would take your 1.4, you have the 900 times, so 900 bits per second per hertz. So it is a leap step in terms of enhancing the area spectral efficiency. And even with 20, you see up to 100-fold improvement. That brings me to the conclusion. The conclusion, I've been working in this mobile communications for many, many years. I started at Siemens in Germany. But around 2000, people when they introduced the 3G networks from mobile telephony, people always have asked about why do we need 2 megabit per link? What's the killer application? And Steve Jobs taught us that the killer application is the app. And now the app is so successful with the smartphones all over that we need to ask ourselves, where is the killer tech in order to be able to avoid the killed app? And that is something that where I think LiFi could heavily contribute. And I also would like to invite you to a presentation later where we have used the NI equipment to show you a visible light link, sending a real-time video over the NI equipment. Thank you very much.